We finished last lecture with the uniqueness theorem. So before starting this, let me just make a correction. In the last lecture, while discussing about the Cauchy's theorem, I made a statement that it is admissible even with finitely many singularities, and use the word removable singularity, but there is not removable singularity. So just neglect the word removable singularity. Just look at that condition that limits z minus z j into f z equal to 0. Okay. Okay, so let us come back to this discussion. So now what we have seen is that the identity theorem or uniqueness theorem. Okay, so now let us see the applications. Okay, so let fz be an analytic function in an open disk delta, which is not identically 0. Okay, so for the time being, let us assume that it has only finitely many number of zeros in the disk delta. So what we did last time is that corresponding to each zero, you have a factorization. So let us count the multiplicities of zeros and repeat the factorization, and you can write it like this. You have only finitely many zeros. So fz, you can write it as z minus z1 into z minus z2, etc. up to z minus zm into gz, where g is an analytic function which is not 0 in the disk. Okay. So this is by a repeated application of what we did in the last video. So you can write it like this. Now you can do a computation to obtain this f dash z by fz equal to this. In fact, this is possible by direct computation or take the logarithmic derivative or whatever. It is possible, but you have to assume that gamma is, you take a gamma which is a closed curve in delta and it does not contain any zeros of f. Okay, and now you integrate over this gamma. Then what happens is that this g dash by g is analytic because g is not 0 and g is analytic. So this integral will vanish and this quantity will give you the left hand side. So now by Cauchy's theorem, this vanishes. Now this happens here. So the right hand side will be quantities like this. So you integrate and multiply by 1 by 2 pi. So this is eta gamma z1, this is eta gamma z2 and so on. So what happens is that you will get this. Integral 1 by 2 pi I integral f dash by fz dz is equal to summation over j eta gamma zj, where zj's are the roots or number of zeros, the zeros enclosed by gamma. Okay. So this is the situation when you have finitely many zeros inside delta, inside the disk delta. Now what happens if you have infinitely many delta, infinitely many zeros? So then also you have the same equation. So what we have to do is that, so suppose you have infinitely many zeros. Now you consider gamma a closed curve which is fully contained in the open disk, but keep in your mind that this closed curve is a compact set. Okay, so you look at the figure. So the compact set gamma is fully contained in delta, and you consider the delta is a disk, so you consider the boundary, I mean the circle. So that's another compact set, and gamma is disjoint from this circle. So two compact sets, disjoint compact sets, so there is a positive distance between them. So use that positive distance to obtain a smaller disk inside delta, but which fully contains gamma. So now you can apply the previous result, because now the smaller disk, so this is the technical part which you can easily, so you have a delta prime. Now you have a new disk which is delta prime, which is fully sitting inside delta, but it also contains gamma. This is possible because gamma is compact and the boundary of delta is also compact. So now in this disk, since it is now it is a compact set now. So in this compact set, you can find only finitely many zeros. Why? Because if there are infinitely many points in a compact set, it will have a limit point, and the zeros of an analytic function cannot have a limit point by our previous discussion, because we have taken f to be non-constant function, okay, non-trivial function. So only trivial functions will have that property. So now you can apply the same thing, and because it has only finitely many zeros, so you can apply the same properties and you get the same identity. That means 1 by 2 pi I integral over gamma f dash z by fz dz is equal to summation over j eta gamma zj, where zj's are the zeros of fz. So now let us see some consequence. But before that, so look at that, this is an infinite sum, but only finitely many of them will be non-zero. So this makes sense. So now in some certain situation, this will give you the number of zeros enclosed by gamma. When eta gamma zj is either 0 or 1 in those situations. Okay. Yeah. Now as a consequence, let us see the consequence. So now gamma under the map F is mapped onto capital gamma. So now put W equal to Fz. So by substitution you will get integral over gamma dw divided W is this. So what happens is that if you multiply by 1 by 2 pi both sides, left hand side is eta gamma 0, this is this is this, and this is the number of zeros and or sum of eta gamma zj's. Okay, that means eta gamma 0 is this. That means the image, so how many number of zeros enclosed by gamma is same as how many times the capital gamma winds around 0. Or in other words, the total number of zeros enclosed by gamma is the winding number of 0 with respect to f of gamma. Okay, so that is very important. Now we apply the result for the analytic function fz minus a, where a is say, an arbitrary complex number. So instead of looking at zeros of function, what you get is that the solution of this equation fz equal to a. So the same thing, you denote the solution to be zja, then left hand side is eta gamma zja, which is this. So here there will be fz minus a because you are applying the result for fz minus a. Derivative is the same because a derivative of a vanishes. So now what happens? This is eta gamma a. Okay. Now we obtain that eta gamma a is same as number of the winding numbers around zja. Now what's the advantage of this identity? Suppose a and b are in the same region determined by capital gamma. That means eta gamma a and eta gamma b are same. Then what happens? Correspondingly, from this equation, you will obtain this. Eta gamma zja and eta gamma zjb, their sum will be the same. So in the special situation, it tells you that number of zja's and number of zjb's are same. That means number of roots of the equation fz equal to a and number of roots of the equation fz equal to b are same under certain condition. Okay. So now we will see some consequence of this result. Look at this. Suppose f of z naught equal to w naught. Now you can choose a small epsilon such that the closed disk around z naught contains only z naught is the only zero of fz minus w naught. That is possible because you know that zeros are isolated. So this is possible. Now you choose gamma to be the circle with radius epsilon, and capital gamma is the image of gamma. Now fz is not equal to w naught for any z belongs to gamma. Okay. Therefore w naught is not in gamma. So by closeness of gamma, w naught is lying outside gamma. So that means in the complement of gamma. So that's an open set. So you can find a neighborhood around w naught which contains completely in the complement of gamma. That is simply using the openness of the complement of gamma. Okay. That means w minus w naught less than delta implies w does not belongs to this thing. So therefore fz minus w has the same number of zeros enclosed by gamma for all w in that disk, because each w is in the same region in the disk is in the same region determined by gamma. So as we obtained just now, the number of zeros of fz minus w will be the same as number of zeros of fz minus w naught. Okay, so they are in the same region. Okay, so what does it mean? So the equation fz equal to w and fz equal to w naught have the same number of solutions for every w minus w naught less than delta in the open disk z minus z naught less than epsilon. So this is a pictorial representation of that. Now, now we chose epsilon such that fz minus w naught has only one zero z naught as a root, but the order of 0 can be n. So that is the same. That order will be the same for every fz minus w. Okay. So for where w comes from here. Now as a consequence, we obtain the open mapping theorem. That means a non-constant analytic function maps open sets into open sets. This is very easy now because you start from an open set. Suppose now omega subset of delta be an open set, and consider f of omega. Now w naught, you want to prove that f of omega is open. You choose a point w naught belongs to f of omega. So w naught is in f of omega, therefore w naught equal to f of z naught for some z naught belongs to omega. Now just now we proved that there exists delta greater than 0 such that whenever you choose W minus W naught less than delta, this equation Fz minus W has exactly same number of zeros as Fz naught minus W naught. Okay, so you know that this has 1 0, so at least this will also have the same number of zeros. That means every W here will have a 0 Z in omega. That means the whole disk is contained in f of omega. So therefore f of omega is open. Another consequence is the maximum principle. This is again very easy. It tells you that a non-constant function will not have, in a region omega, the absolute value of fz will not have any maximum in omega. That's easy because you take any W naught in the image and it cannot be a maximum because W naught is here in the image, and we have already seen that a disk around that will be fully contained in omega, f of omega. So therefore, in this disk, there will be several elements with absolute value greater than W naught, absolute value of W naught. Therefore, any W naught here cannot be a maximum. So we will use this maximum principle to obtain Schwarz lemma and several other things. We'll come back with those things in the next.